Okay, thank you very much. Thank you very much for having me here. It is a very humbling moment for me, to be honest. So first of all, this room is a very humbling room, the room of God, where I'm just obviously very academically shaped here with all these books. But second, for me, as a computer scientist, do not underestimate how hard it is to stand here in front of experts in meteorology, trying to apply the half knowledge that I gained the last 10 years talking to people at Meteo Swiss and other institutions close to me, like Xavier, for example. So please bear with me. I'm a computer scientist. So if I say anything kind of silly in meteorology, let me know, but maybe let me know in the break. So just walk up to me. Okay, so let me get started. This is Switzerland. Switzerland is beautiful. We just learned I'm coming from Switzerland. The Matterhorn is one of those mountains that actually has an interesting effect. It forms these banner clouds, as you can see here. And I'm sure you're more familiar with banner clouds than I am. So why am I showing you the Matterhorn? Well, I'm showing it to you because that is one good example for showing the effects of grid resolution, which probably many of you know, at least as good as I do. So the question is really, is it going to snow where the banner cloud formed? So that's quite important if you're a mountaineer, or if you're a hobby mountaineer like I am. And then you look at the discretization of the grid here, and it's about 35 meters, and you can still see the Matterhorn. But now, as we're going to refine, actually coarsen the grid, you will see that mountain unfortunately disappear. And whoever has been there, you see that this is quite a massive mountain. But even on a 1 kilometer scale, which many of us are still trying to get at a global scale, and many have at a local scale, it is nearly vanished. It is, by the way, about 100,000x in compute away from what we want, the 1 kilometer scale, in order to resolve that mountain reasonably to predict these clouds with the physical effects. So that's unfortunate. So Meteo Swiss is using a 1 kilometer model. I learned yesterday that the DVD is using a 2 kilometer model. Of course, there are no such mountains like the Matterhorn in Germany that need to be resolved. But still, I mean, the difference is not that big in some sense. Okay, so we are really about a factor of 100,000 away in compute from where we want to be. So how do we get there? Well, you could argue that we could just wait, because we've been waiting the last 30 years. Right? Waiting is a good strategy for computer science if you want to get stuff faster, because there was a thing that's called Moore's law, where you just every 18 months, the number of transistor doubles, blah, 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 you know all of this. So you just wait, essentially, and things will get better. Now the question is, well, is this waiting, will this pay off in the future? But talking about the future is always a little bit problematic, because now there are widely varying predictions about the future. In the same week, at the end of 2022, about a year ago, both NVIDIA and Intel CEOs or high-ranking officers said that Moore's law is dead and Moore's law is alive. So that's an interesting one. So I'll let you judge this for yourself. I have a particular opinion on this, but I'll give you some data. I always like data. So I'll give you the stock value development of these two companies. Just for your entertainment, I'm not labeling those. So this is about 2019, they had about the same value. So one of those companies is now a factor of 10 more valuable, and the other company is a little bit less valuable than it was in 2019. So one of those said Moore's law is ending, one of those said Moore's law is continuing. My stance is that Moore's law has most likely ended because of an economic argument. Because what most people forget in Moore's law is that Moore's law says that we are actually doubling the number of transistors, and those transistors do not get more expensive. And that is unfortunately over. So we can still increase the number of transistors. We don't double them in 18 months, but they get more expensive. So we actually have to pay for them, which is a pain, because now waiting doesn't pay off. Waiting just allows you to spend more money on the same compute now. Well, you know, that's something that we don't necessarily want to do. But now there's some interesting second effect. I talked about weather prediction here, but actually climate prediction is much harder. And here I want to motivate a little bit more what we could do there to predict the future of the Earth. This is a summary of a meeting that we had in Berlin, the Earth Virtualization Engine meeting, where we tried to figure out what could be a good strategy going forward. We wrote a paper on this, a technical perspective down here, and this is an excerpt from that paper. So what do we do? And again, here I'm the computer scientist. Any meteorological artifacts in this presentation, please let me or Björn Stevens know. So as we increase the resolution, we will actually resolve more physical processes, right? It's hopefully relatively clear. At the very high resolution, at the very coarse resolution, 100 kilometer, we don't see a whole lot, we don't resolve a whole lot. But apparently at 25 kilometers, we begin to resolve extremely large eddies, like eddy calculations like cyclones or eddy effects. Then storm resolving is starting at around 1 kilometer. By the way, I had a wonderful discussion about what resolution versus grid spacing means yesterday. That is not the same thing, as I learned. Apparently in ICANN, there's at least a factor of 4 between those two, but I don't want to go into too much detail here. But then at about 100 meters, we resolve a whole lot of smallish clouds. So here, this is the gray zone where we really want to get to increase the accuracy of climate simulations quite substantially. But now this is extremely expensive, as I mentioned, especially at the global scale. So this is expensive in 2 dimensions. So one dimension is the storage, where here there's an additional line, which is approximately the storage for one trajectory. Is a reasonable set of variables goes up to 50 petabytes, and that's just one trajectory at the 100-meter resolution. So we are talking exabytes if we do ensemble simulations, and that is, of course, a problem here. Now, talking about ensemble simulations, if we now look at the ensemble members we can simulate at 1 simulation year per day. So in about 1 month, we can simulate 30 years, which is a short climate run in some sense. And if we now fix a single simulation, we can draw interesting lines here. We can first of all realize that laptop scale compute is in the very bottom left. So this is something you can do on your laptop today. Then you can look at the CMIP6 and high-res MIP simulation runs that we all know. And then you can actually draw these vertical lines here, not vertical, but kind of, vertical / horizontal lines, where supercomputer performance lies on this scale. So 1990, 2000, 2010, now we're getting into the 2020s where we can put real names on it, and you will actually recognize, like the Levante system in Germany, the LUMI system, and the Frontier system, and the Fugaku system, which is a prediction that colleagues at DKRZ and MPIM, like Claudia and Floria and Simon, helped me to get to. And here we see the intercept of these systems. So this is an estimated curve for Frontier and Fugaku. We see that today for one on a single simulation, we actually get kind of close-ish to 1 kilometer resolution, but of course we need more than one ensemble. So, and everything up here is there be dragons. So this is something we cannot compute today. So we want to get there. Now, what we discussed at EVE, one potential target would be here. Small number of ensembles, so less than 10, 5-ish, and 1 kilometer resolution. I'll tell you why we believe we can live with about 5-ish ensembles less than 10. But first of all, what can we do? Well, we can build faster supercomputers. This is what we've been doing the last essentially 30 years. This is the 20th instance of this workshop. So we are actually looking back at quite a long history at ECMWF, and we've seen all these wonderful plots yesterday, how we can get to higher performance by building faster supercomputers. What we can also do these days, we have a completely new technology up our sleeves. We can use machine learning to somehow break that boundary. So for example, as I'm going to tell you later in the talk, we can use machine learning to replace ensembles much cheaper. So we can pump up ensemble density. And I'll give you 2 different approaches for this. But what we could also do is we could optimize the program to move along this scale to enable higher performance at higher resolution. Or we can also use ML approaches to do this. And this is another thing I want to give you a little bit more insight into in this talk. So we're still at the overview of what I'm going to talk about. So now the question is, well, we had this small number of trajectories, and many of you probably know, actually most of you know because you're meteorologists, or most of you, that you need more ensemble members to get a good sample of the distribution of the weather, which is very often called climate, in the future. So 5 is probably not enough. There's a very particular idea which goes back a long time, where you could think about how could you use a smaller number of ensembles. For example, here you have a times going from 0 to a time step 0 to 30 just randomly, and you have one trajectory that moves through that state space here. That, of course, is represented by a 3-dimensional field and blah, blah, blah. So it's just one trajectory. You may be able to compute a second one. But now if you want to get to 50, which is the ensemble size that ECMWF, actually, I don't know if it's still true today, but a couple of years ago used, that is going to be extremely expensive because we've seen the single run at 1 kilometer is super expensive. So we cannot afford many of those. But what we can do is we can actually run many machine learning predictions that help us sample these trajectories a little bit better to get a better understanding of the probability distribution of those variables, which in black are what many people call deterministic simulations. And then in colored are extremely cheap machine learning predictions, which today we know how to do at about a factor of 1,000 to 10,000 cheaper, but of course at a very limited horizon. But what can we do? Well, we can start at t equals 0, run the simulation, and then run it only until t equals 10. And then start it there again from the base of a deterministic simulation that we've been running long-term physics-based forward. So we combine data-driven and deterministic simulations in a principle that Björn Stevens calls tethering. I would call it ensemble boosting, but yeah, we can discuss the name later. So that is something that we could consider on the algorithmic side. But now I want to motivate a little bit more of this talk what actually has been changing in high performance computing the last years, because we are at the edge of a massive change that will lift us or leave us in a bad or a good place. So it may either lift us to a good place if we manage to embrace it, or we'll be left with something that we may not be able to use, or we may not be able to grow with. So what has happened? Well, who's heard about ChatGPT, right? So it's kind of, there's no talk without ChatGPT. Actually, that's only true that yesterday, most of the talks were without ChatGPT, which is very funny, because at computer science conferences, you don't get away with this. You have to at least mention the GPT models once in your talk. So the funny thing is that these language models have shown extremely surprising capabilities. So they could be your lawyer. Actually, they could really be your lawyer. They could be your business administrator. They could be your doctor. And if they are your doctor, you would most likely prefer them to a real doctor. There are questionnaires that actually doctors prefer the answer of language models to the answer of real doctors because they show more empathy. And if you've worked with these things, you will know they show sometimes a little bit too much empathy. But 71%, I can send you the study. Actually, ChatGPT may take your job or my job and even make more money working for Google. So that's an interesting one. And now what has changed? Well, these models are trained on massive supercomputer architectures. So now Facebook, a company that does social networks, right? So it connects people, builds one of the most powerful supercomputers on the planet, Facebook. How does that make sense? Google, a search engine company, builds one of the most powerful supercomputers on the planet. Microsoft, a software company, builds one of the most supercomputers on the planet, and I witnessed this, I have helped them. They have a very large machine. And even worse, oh, I don't have that slide, I guess. No, I do. Tesla, a car company, builds one of the most powerful supercomputers on the planet. In fact, Tesla builds their own chips to do this. They built their own network, they built their own AI accelerators, they built everything. So what is going on? Well, what's going on is that this workload, this very simple text interpretation and text processing workload, which I don't have enough time to explain here, and I just want to skip this, but this iterative process of training an extremely large neural network is taking over. So, but what does this mean for meteorologists? I mean, yes, we could use this. We could ask a thing about weather, and in fact, we've done this. It's a very interesting paper forthcoming with Peter Bauer and Björn Stevens on this. But that's not what I want to talk about because we're at the HPC workshop. We are not about the talk to the language model about meteorology workshop. So what does this mean for HPC? Well, we're going towards a more than $1 trillion market. Okay, that's a number that takes me a while to understand. That's 1,000 billion. It's 1,000 million. That's a lot of money. That market will create a gravity well that everybody is going to be pushed towards or pulled towards. What does this mean? Well, we'll basically be seeing most, if not all, of the microprocessor companies optimizing for that market and potentially that market alone. Right? So the HPC market is about a $10 to $50 billion market. That's a 1% digit fraction of this market that's coming up. Okay, we just need to be careful here when we talk about HPC. Okay, good. So what does this mean for us? Of course, these things are supercomputers, so somehow they seem very similar to HPC because we've been building supercomputers for the last couple of decades. Suddenly, companies build bigger supercomputers than we do. How are they different? They're different in three major features that we need to understand how to embrace. Small data types, they're significantly faster than larger data types. There's a lot of movement here at the ECMWF and many other institutions going towards smaller data types. But hey, FP32 is not cutting it. FP16 is not cutting it. So we must try to go even smaller, which is of course a huge numerical problem. I understand it's not so simple, but at the end, many deep neural networks manage to do it, and those networks perform reasonably well at some aspects of predicting the future weather and climate. So we need to figure out how they do it and apply this to the constraint of physical equations or replace pieces by learning. And I'll give you some more insight on this later. The next thing is they perform matrix and vector operations very, very optimized. So unfortunately, not so great for stencils, which is the underlying primitive that many of us here are using. And the last one, it's maybe not so relevant today, but I believe it's going to be much more relevant later, is sparsity in the data, sparsity in the computation. What NVIDIA calls structured sparsity, which is I don't have enough time to explain it, but this is this 2 to 4 sparsity. And again, if you care about the details, we can talk about this in the break, and I'll be here until at least 2 p.m. today. So now this means that this multi-billion-dollar hardware industry, which launches that trillion-dollar market, mostly driven by NVIDIA actually, but Google has some cool ideas in their sleeves as well. Then there are other companies that drive this market or try to enter this market basically. And then there are a gazillion startups that are really looking to make a big benefit or be acquired with that market, which is also something to consider when we are going forward into the future. So I've seen talks by GraphCore here and other startups that are potentially there. So now let's go from the hardware background. And now we understand that the trillion-dollar market will be driven by a multi-billion-dollar hardware industry that is solely focusing on deep learning. So how can we take advantage of this as meteorologists, as us trying to present or predict the future of either the Earth or the near-term future of the Earth or the long-term future in terms of climate? Well, I see 2 approaches. So one potential approach is you could accelerate simulations on the simulations like we have today, on the hardware that we are going to have tomorrow. So I've seen many talks yesterday talking about how to get on GPUs. But hey, GPUs were introduced more than 10 years ago. Talking about today how to get on GPUs, I mean, the train has, maybe a little bit late, so we need to be fast. The next generation hardware will be GPUs with machine learning accelerators. Right? They will be GPU-like. They will be called differently, like IPUs if you're GraphCore, or XPUs, or APUs. There are so many different names for this. But it's really these 3 principles that I showed you before: small data types, matrix and vector operations, and sparsity will be predominant in those architectures, will be extremely fast. Okay, so here are some challenges that you can read yourself. I don't like reading slides. And then the other thing we could do is we could just say, hey, screw all the simulation, these equations, who needs them? Because we have things like Pangu Weather, GraphCast, ForecastNet that have wonderful properties for predicting the future. I'm exaggerating here because most of you are, or many of you are skeptical. And I agree, but they have a lot to them. So we could embrace those models as well to either replace simulations completely or replace parts of the workflow. So, and I want to stipulate a little bit replacing parts of the workflow in this talk. So it's really 2 things that I want to talk about. One is the systems challenges. How do we get GPU, potentially AI accelerator support better? And the second one is, how can we use machine learning as part of the workflow, not replacing the whole thing? I'm not going to talk about models that replace the whole workflow, but really focusing on the post-processing workflow, the simulation data. So we're talking about accelerating the simulation and then the post-processing with machine learning. Okay, now I've seen a lot of talks yesterday, talked to a lot of people, and I've been adjacent to the community, let's say, for the last 10 years, and had a lot of discussions through my local friends in Zurich, what to do exactly. You all know the history. We pushed Stella, we pushed GT4Pi, and then a large part of the community actually went for a slightly different approach, which is Pragnos, or the path of least resistance at the beginning, I would call it. So you take your code and you add annotations to your code. And of course, what am I telling you? I've seen many talks yesterday embracing that principle. So now if you look at this code, and I don't want to disclose what that code actually is or who the authors are on purpose, because I'm going to say some negative things about it. So if you look at this code, everything in here that's black is the original Fortran code, essentially. So this code that people may have been writing decades ago, it still looks the same. And then everything that is in red is an annotation that tells the compiler about properties of the black Fortran code. Like this is really what it does. You tell the compiler, you assert to the compiler, actually you're not telling it, you assert to the compiler that the Fortran code has certain things. Now there's a difference between OpenMP5 and OpenACC, which is the level of assertion, right? So how do you assert things? But I don't want to go into too much detail because both of those are kind of the same. I'm picking a little bit on OpenACC here, but that's just because it seems like all the codes I'm looking at in this community are using OpenACC, but you can make the same argument for OpenMP. So what that means is now we have to look at all of those. So there are certain problems with this. So first of all, you have to learn another language, right? So you know Fortran, and now suddenly you have to learn a second language. But that's not a big problem because learning is a good idea. It's always great to get better. But then from a software engineering perspective and maintenance perspective of the models that you're extending with such languages, there's in fact an ISO norm for code maintainability. ISO 9126, you can look it up, and it has four measures of code maintainability, which is how easy it is to analyze, how easy it is to read, how easy it is to change, how stable it is, and how easy it is to test. And then this paper up here looked at various source code properties to see how they influence these four metrics of code maintainability. And I want to just look at one of those, duplication. Because what we are essentially doing with these languages, with these annotation languages, is we duplicate code. We have the loop here, but instead of having the loop express what it does and what the properties, what the constraints are, we add additional independence assertions. We say, hey, that loop is independent to the code. That's a duplication, right? What does that mean? If I'm now changing anything in here, and I swear I can change 2 characters in this loop, and the loop will not be independent anymore. And you can now guess which 2 characters these are. There are probably multiple solutions to the riddle here. And then this assertion is broken, and you may not even realize it. So which now means if you're a climate scientist, and if you want to change your source code, you change your source code, but at the same time, you have to double check if all these annotations are still correct. So that's a bit of a pain, especially if you try to separate the roles of the performance engineer from the climate scientists, which I'm actually seeing here, which is a very wise decision. So you have people writing these annotations, and then you have people writing the actual meteorology code, which are mathematicians or meteorologists. So that's a huge pain. But now, the same code in another file has this. This is in another file. It's even worse. So somehow it tells you properties of the arrays to be expected that show up in another file. So now you already need to look at 2 files. And actually, if you look at that particular code, that code has 6,440 lines of code, and 833, more than 10%, are OpenACC annotations. Now you say, well, I don't care about that code. Well, I did the math for Icon. So Icon has about 3% OpenACC annotations, so 3% of the lines of code, which sounds much less than this. However, we have to also see that Icon does not have OpenACC everywhere. It's essentially the atmospheric calculation, as far as I understand, is OpenACC at this point, maybe a little bit more. Okay, so this duplication, I just wanted to make that point and not elaborate too much. So what is the solution to this? Well, the solution is to not duplicate the code, obviously. The solution is unfortunately a little bit more, gives a little bit more resistance. So we've seen some approaches yesterday. So we've seen this Loki source-to-source compiler, which is a potential solution to the problem, which I find a complicated solution in some sense because you have to work on the AST. So it's an AST to AST transformation framework. Getting the dependencies from an AST is quite an advanced art. So high respect for the people working on this problem because it is actually quite hard to do, at least in my experience. So what are we trying to do? We are trying something very similar. We just compile the source code into an intermediate representation that allows us to easier look at the dependencies, to easier figure out what's independent and what's not, and then emit code in potentially a completely different language. I mean, for us, it's always C++. So that's what we call performance metaprogramming, but let me explain you a little bit more how it works. So we have a domain scientist. Domain scientist works on DSLs or, I don't know, Python or whatever language you like. And I'll tell you a little bit about Fortran in a couple of minutes. So it could also be Fortran, even though it took quite a while to convince my computer science colleagues, like even though they're reporting to me, to work with Fortran. So then you have an applied scientist that really does what I just mentioned. The applied scientist translates the input program, like the meteorology code, into an internal representation, which is in our case graph-based. So it's a program graph. This program graph is not recognizable to the domain scientist and should not be, because it's recognizable to another person that is called a performance engineer in our setting. And that other person has, again, no idea about meteorology. So we completely decouple the two. The big benefit is that the meteorologist can remain working at the meteorology side, does not even see annotations like OpenACC in the code. They're not existent. And the performance engineer works on a representation that is natural to the performance engineer because it gives you all of the dependencies in the code as a graph representation. And then the performance engineer just emits CPU, CPU, GPU, and FPGA code. So that's all jolly, Roger. It's all happy. What does that mean? Tens of lines of code I want to use to describe a problem. Which community has succeeded? Actually, it's quite funny. We started earlier than the machine learning community working on this. The machine learning community has passed us in this approach. The model underlying ChatGPT, the GPT model, generative pre-trained transformers, you can write it down in about 25 lines of code. The model that drives the $1 trillion market, let me repeat this, is about 25 lines of code in PyTorch. Right? And I've seen it, we run it, it's great. Underneath comes all of that performance engineering stuff, because it runs at the end of tens of thousands of GPUs. You could argue that problem is much simpler, and I would agree. It is much simpler than what we are talking about here. But then what we are proposing is that we have these performance engineer write programs that take an input program here in this graph representation and output a new program that is optimized in the same graph representation. So this is what performance meta programming stands for. I'm writing a program that transforms a program from representation A to representation B. Why is that good? It's good because you can match a certain pattern in your original program, and if it applies, you output a new optimized case. It's like library matching. Now, if the domain scientist up here changes something and this pattern does not apply anymore, well, it's great because then the optimization doesn't apply anymore. Then you tell your performance engineer, well, obviously there's now a new pattern to be matched. Go write a code for this. So we have completely decoupled these two roles again based on the pattern matching in this, what we call parametric program graph or stateful data flow graph. So, and at the end, we were generating thousands, but actually it's more like tens or hundreds of thousands, unfortunately, lines of code that you don't necessarily want to look at. Yesterday, we've had the question of if the low-key output is readable. The answer was yes, and that's great. Our output, we would also claim it's readable, but once you have tiled your loop in 200 different ways, you can still read the code. We have wonderful indentation, but you don't want to read the code. You really don't want to. You want to work on a different representation that is not machine-oriented. I mean, asking the question if some optimized representation should be readable is like the question, should assembly code be readable? No, it should be machine-readable, but maybe not human-readable. So the humans work here. Okay, wonderful. So back to Fortran, because every source code I've seen yesterday was somewhat Fortran. So Fortran, why is that not, it doesn't sound so bad, actually. Many scientists like it, I like it. Well, I'll crack some jokes on Fortran in the next couple of minutes. So actually, my liking of Fortran seems to change every week. So one week I think it's a good idea, then I look at a lot of Fortran code and it's like, oh my God, how can you write this? And it keeps going back and forth. Last week I've been reading the icon code, so I am a little bit cynical about Fortran this week. So next week, ask me again and I may have changed my opinion. So if you just look at this code, well, what is a problem? What's a potential problem in Fortran code? Well, first of all, the domain size is everything is just embedded. Everything is fixed as constants. The loop order is fixed, right? So somebody chooses a loop order. Basically, most of the optimizations that we talked about yesterday, I mean, you guys are smiling, is exactly the loop order optimization, right? We need to figure out the loop orders. We need to change the loop orders. In Fortran code, it's a pain to do this because you may need to go through hundreds of files and change the loop order in these hundreds of files. The schedule is fixed. So what comes first is fixed. The order of execution is fixed. So we heard about functional, somebody was asking a question about functional parallelism yesterday. That's just fixed in the code, but of course, functional parallelism is a thing, so you may want to do it. And even worse, that's probably the biggest problem in Fortran, the memory layout is fixed. Had wonderful discussions yesterday night about memory layouts of Fortran, strided access, I don't know what. That is also just very painful if you have to change that in the code directly. This is why people come up with a source-to-source translator, because this is where you can do it reasonably well. The other thing is tiling strategies, which is our biggest problem. When we optimize a code, the first thing we do is to undo the tiling that you guys have done. because we want to get to a canonical representation from which we can optimize to a specific architectures. So actually for performance engineer, if you already have too much tiling in your code, it is not a great idea. And many, many more. I could be going on 5 more minutes. But what this really boils down to is 2 things to say about Fortran. The hardware details are fixed in the language. There are annotations that try to relax those by asserting certain properties of the code, but at the end, the code that's written fixes the hardware details. It's a very low-level representation. And unfortunately, the ecosystem of Fortran is weakening over time because the interest dwindles in the industry and everywhere else. And machine learning, is not going to use Fortran. And this $1 trillion industry will attract 99% of the students. I had not had a single student apply the last 2 years who did not mention machine learning. So, and I'm in high performance computing, which is technically something different. But so if you now want to map all of this to all these different architectures, here's a Cerebras logo, A64FX we heard yesterday, then this may be a little bit of a pain for the scientist because you now need to change potentially all of these things. So now let me introduce an idea that we had a long time ago in Switzerland, and most of you will know about is the GT4Pi grid tools / GT4Pi idea. GT4Pi is literally just grid tools ported to Python because Python is the new thing coming from the $1 trillion market and everybody cares about it. And here in the context, I want to mention the PACE project. And I don't want to talk too much about it because there's a wonderful talk this afternoon on PACE. I don't want to steal the thunder. But I want to just introduce it enough for the sake that you can follow my presentation for the next couple of minutes. So PACE is really taking the FV3 NOAA model and well, get it to run on modern supercomputers by rewriting large pieces of it, or basically everything, in Python without the involvement of Fortran. And the idea is not necessarily performance first, but is actually ecosystem first. So if you talk to Oli, a good friend of mine, Oli Forer, he's going to emphasize the DevOps, the management, and really the development environment. And this is where I completely subscribe. Because you can say it's faster, but then if you tune your OpenACC code enough and add enough ugly annotations, you'll get the same performance. And so there's no, the performance is no magic. You can do it. The question is, what is the price you're paying to get to that performance? What is the price you're paying on the back of your scientist who then may not be able to read the code anymore once you have applied all of these optimizations? This is the typical thing in HPC. Okay, so what they did, and again, this is not our work, this is the work that's also cited down here by AI2. So they translated the 29,000 lines of code into 12,000 Python lines of code, which to me was quite shocking because I was first thinking I would hope that it goes down a factor of 10 the code complexity. I mentioned the 25 lines of code for chat, the underlying model for ChatGPT basically. So here we have a factor of 2 because the DSL is still quite birdy if you look at it. So that is maybe something we may want to improve, but that's not in my, it's above my pay grade, I would say. So they have remapped all of these pieces, which you know better than I do. Here the infrastructure is now GT4Pi, so it basically sits on top of that Python module. And here's where we come in. We have a backend for GT4Pi that is our performance metaprogramming approach, which we call DACE. So if you see that symbol, it's that. So we orchestrate the thing with local optimizations. Then we have a thing that we call transfer tuning. Then we do full program optimizations where we lift local optimizations through transfer tuning to full program optimizations. And I'm going to present this in the next couple of minutes because that's actually quite a cool technique, which is automating what I said earlier, what the performance engineer does. So this is the overview, and I'm going to focus on this lowest piece here. And I'm assuming later today you're going to hear more about the upper piece. And so please stay. So again, this performance metaprogramming principle. Once we translated the GT4Pi code, the 12,000 lines of code, into a graph, the graph is going to look like this. So the screen doesn't have enough pixel to actually show me all of the elements of the graph. Well, so it's a complex program, and this is going to be not so easy. So we can zoom into this graph, then we see more structure. We can actually zoom more into this structure, and then we see more structure. In fact, you can zoom into until you see the source code, which is unfortunately still too small to be read on this slide. So that's a bit of a pain. Again, even if you're a performance engineer, you would have to look through 12,000 instances of this, 12,000 lines of code graph with, I believe it was something like 6,000 vertices or something like this. So how do we deal with this? Well, the way we deal with this is we take primitives where we look at subgraphs that you could tune in certain ways. So we extract representative subgraphs from this graph, because much of these calculations, or many of these calculations, are covered by a small number of what I would call primitive shapes or primitive patterns, like the stencil pattern, or actually it's more like a stencil chain pattern, multiple stencils depending on each other. What we do then is we do an exhaustive tuning on these what we call graph cutouts. So these are just little graphs, little pieces of your code. The graph is representing the code. So we do exhaustive tuning, looking at all possible variants you could generate, so tens of thousands of code variants, and store the top K variants. I think we just remember the top K performing variants. What we do then is we apply these transformations to the full program based on a similarity metric. So we look at a subgraph, we get to an embedding vector for that subgraph. Now it's a little bit machine learning, but it's kind of a representation of the shape of that graph. And then we see which one of those transformations is closest to that subgraph, and then we apply those relatively blindly. Okay? And then what's nice, we can reduce the search space, because if we were automatically looking through all possible fusions of the FE3 graph, we would get 30 million configurations. So 30 million configurations is too much to compile and run. And after doing that, we get down to 600. And with the 600, we actually can run the whole transformation in about 8 hours. So the compilation takes 8 hours, right? So it's still not the performance compilation. The normal compilation takes minutes, but if you really want to optimize the performance, it takes about 8 hours. Okay, so what does this lead to? Well, let me give you some performance results on the Pitt-Stein machine. We also have results on the Joules Booster machine. If you care about, you can read this SC22 paper, or you can actually watch my postdoc's talk, Tal, and get many more details. But first of all, on this Pitt-Stein machine, it is a machine where we can compare a relatively old CPU with a relatively old GPU. But this transfers to more modern things. What the main difference here is the memory bandwidth. The CPU has about 40 gigabyte per second memory bandwidth, and the GPU has about 500 gigabyte per second memory bandwidth. That's a factor of 11. So many people say the codes we're working today are very memory bandwidth limited, which I would not really say today, but most people assume this. So we can talk about this more in detail, why I believe this is kind of a misleading statement in many ways. But we get a maximum speed up if you just look at the memory bandwidth bound by about 11. So now if you look at some representative solvers, like for example, a Riemann solver in that implementation, we see here growing domain sizes from relative size 1x to 9x. We see here the original Fortran code, which is a really well-tuned code, by the way. So the original FE3 code is quite nice. And we can see the scaling, how it goes up from 12 to about 9. So we even get a little bit a super linear scaling with no, it slows down a little bit. I apologize. We lose about 10% performance here. And at the end, if we do the GPU case, GT4 pi plus days, we get a little bit 8 because we are running out of parallelism on the GPU as well. Well, okay. So we get a reasonable speed up for that guy. Now let's look at another horizontal stencil example. Here, actually, in this domain, 128 by 128 by 80, which is a domain that you may want to run for operational weather forecasting, you have very little misses in this code. This is why I'm not so sure if we should call this really memory bandwidth bound. It seems to be more bound by the internal properties of the microarchitecture of the particular CPU that's limiting the performance, unfortunately. So this is not really the memory bandwidth. But for the larger domain, we're somewhat falling out of cache, as you can see. With a 9x larger domain, we get a 30x larger runtime. And the nice thing is here the GPU shines, because GPU with a 500 gigabyte per second memory bandwidth is actually closing that gap much more efficiently, like in the previous case, because here it shines in the memory bandwidth. We still don't get the 11x, by the way. The icon implementation with OpenACC gets about a 6.5x speed up as documented in 2022. So we get a slightly higher speed up on the exact same system. So at the end, the application speed up here is 3.9 for the end-to-end application, but it scales up to 2,400 nodes. So it actually works reasonably well. And we get to 0.12 simulated years per day at 2.6 kilometer spacing for a really old machine. And that machine is about 5 years old. Okay, nice. So what did that mean at the end? Well, we invested about 6 weeks of work with 10 optimization revisions and only 4 performance engineers to really optimize that whole code, like the whole original 29,000 lines of Python code, we get a speed up somewhere between 4 and 8x, depending on what part of the code you look at. The average speed up across the whole code, you've seen it, is about 4, 4.5, depending on the exact. There are 0 model changes. So we made it a religion to not change the input code. Right? The input code is exactly the same. So we don't do anything there. But if you care more about details on that particular work, I would recommend watching the talk by Tal, which is on our YouTube channel. But now, that's all nice, but do we really want to rewrite all of our codes? Because some of you look like, oh my God, now I need to rewrite all my codes in Python. Yesterday, I learned that IFS is more than 1 million lines of code. ICANN is about 500,000 lines of code. If you look at average programmer productivity, that's going to take decades to rewrite this into a different language. So maybe, at least for the old code, we want to take a second look at Fortran, because otherwise it may be a huge investment. So now if you step back a little bit, what are these DSLs? So these DSLs, and I'm again listing some of them here, are really built for productivity and portability. Right? So many are built for productivity. So like all the Python-based DSLs, usually you go for productivity. Other DSLs that come from the HPC space, like Raja and Kokos, they focus more on performance portability, not so much on productivity. So the machine learning field has embraced Python because their productivity is much more valuable, at least in the early stages of model development, than performance. Typically how it goes, you test a lot of models with very quick turnaround time of data scientists, and then you optimize one of those models that is successful to the real machine, and then you run this on 10,000 GPUs. But first you run it on 1,000 GPUs, which still is a lot, but very inefficiently in some sense. So this is the how at least in Microsoft people work. Okay, so now if you could look at this more from a performance portability perspective, you could argue that many of these languages somehow up-level library interfaces, because if you're able to use performance library interfaces, it's all great. Like if your calculation is all dgem, you don't need to do anything. You just call dgem. But now the problem is your calculation is more complicated than dgem. This is why you introduce a DSL to capture more complex, to make it more flexible than dgem call. Okay, but then if you actually look at it, at the end, we're all manipulating arrays with scientific formulas. Well, and there is really only one language that has a name formula translator in it. And that's called Fortran. So in some sense, Fortran is the oldest DSL that has been designed for manipulating arrays in a scientific context. And actually, Fortran is not so bad. I mean, it's back in the top 20 programming languages, if you want to say something positive, and that was in 2022. No, sorry, 2021. Okay, that may have changed by now. Actually, if you look at the TIOB index, it is growing. So it is growing. It's on rank number 20 so far. So it's not, you could argue there have been worse times. However, I personally still have doubts about the future of Fortran, the ecosystem, productivity in Fortran. But let's be pragmatic here. Okay, so again, I change my opinion every week. So if you ask me next week, I may be more positive. Let's look at ECMWF's Cloud SC. And I see many of the authors here. It's wonderful to finally meet you guys in person. And so ECMWF has written that code to represent column microphysics, which we've heard everything about yesterday. And I don't want to repeat any of this because there were wonderful talks yesterday. So it's about 2,500 lines of code in Fortran 95. It was rewritten for portability, and the optimization apparently took months for really good performance engineers. And if you look at the code, it's this here. And actually, that's just the initialization variable setup code. And it continues until line 500. So for a computer scientist, that is just OMG. I mean, how can you work in that environment? But yeah, fine. So you can compile that code. A compiler actually runs it to Fortran. You get a 1x execution time here. That's fine. Then if you run the original ECMWF version, it is significantly slower. So it breaks my C programmer heart a little bit. But then we applied our tool chain to it. So we have a Fortran front end that runs it to this performance metaprogramming thing that I mentioned earlier. And now if we run it to ours, our tool chain actually emits C++ code that is optimized. It's a little bit better optimized than the C reference version. So it's 90% as fast as the Fortran version. Oh, that's still sad. However, if we run it on 32 threads, we get slightly faster than the Fortran version because we do slightly better adjustment of the OpenMP parallel regions. So that's great. But also, we can run it on a GPU. And in fact, on the GPU, we get 100x speed up over the original one, and we're just slightly slower on than the OpenACC version. However, as of last week, we are actually slightly faster than the OpenACC version because we match the exact performance of the CUDA code. Because the CUDA code implements K-caching, which I just learned is a completely trivial concept, but everybody in my group talked about it as if it was really complicated. So we just do that as a performance meta program and actually match the hand-optimized CUDA code. So now we are on to make this even faster. And this is all from the unchanged Cloud SC Fortran code. Right? So there's no change, like no single character is different in the unchanged, in the Fortran code. And thank you very much, Christian, for supporting us with that, setting that up, and everybody who helped in that environment. Cool. So with that, I would like to kind of finish with this, finish the first part of my talk, which I extended yesterday because I attended the day yesterday and I thought I should talk a little bit more about HPC and a little bit less about machine learning because everybody yesterday was talking about HPC. So I thought I would emphasize this a bit more because people may appreciate it, and I see many people smiling in the audience appreciate the pain. So I now want to go to using MLAI techniques to replace parts of the workflow. So this is a post-processing in the simulation data. Here I am much less certain of what I'm talking about because this is now entering a domain science I'm not necessarily super familiar with. So see this please as coming from a computer scientist who tries to help. So don't immediately pound with a stick on me if you see something that is that may be strange. So Björn Stevens would call this ML on top. So ML on top of the simulation in some sense. Okay, so now we all know forecasting has uncertainties. I don't want to go too much into detail. We also know trajectories of hurricane predictions have uncertainties and blah, blah, blah. Weather is a chaotic system where minor effects can perturb larger things. The solution is, or a solution is to try to capture the uncertainty through ensemble simulations. So that's an obvious thing you can do. You just run multiple simulations with slightly perturbed starting conditions. ECM.F is doing this since a while. There's actually a wonderful wonderful illustration that we just stole from their webpage, but of course we credited them here. Yes, exactly. So how does this work at ECM.F? Well, we have these 51 ensemble members. And again, since you're all the experts here, I don't need to repeat this. So 50 are stochastic, 1 is deterministic. So there is a trade-off between the resolution between slightly lower and slightly higher, because of course, if you run many ensemble members, it's going to be many times more expensive. So it's 50 times as expensive as the deterministic one. So you can run the deterministic one at slightly higher resolution and run the non-deterministic, so the ensemble ones at lower resolution. So now you could keep that economic argument and go further and say, well, what we are actually interested in is this probability distribution in the forecast. So can we get this probability distribution with another means? Well, actually, yes, we can. And there's even a poster downstairs how to do this. So we've done this a relatively long time ago. But we basically predict mean and standard deviation of this distribution from a smaller ensemble size with less members. The second thing is, I hear the rumors, and I'm not sure if they're true, that there's a certain bias in the ECMWF models that is not necessarily representing the actual weather development, but I'm not sure. That's a rumor. But we could also try to learn the local model bias from observations, right? So there are two different ideas. One is to predict the spread better, the probability distribution, and the other one is actually to predict the center of the probability distribution and to move it in case the model has a certain bias, right? And the models that we're looking at, they have a bias. And we do this all with deep neural networks, and this is relatively simple. So here we have a data set that we extracted with the help of Peter Dubin from ECM.F, this ENS10 data set. And we actually made it, so this is, let me just skip these animations. So together with the ERA5, so this is a simulation data set, this is a reanalysis, as we all know. We use ERA5 always as a ground truth. These are all the ensembles, 10 ensemble members from ECMWF, so 10 out of the 50, we chose random ensemble members. And then we look how the ensemble prediction compares to the ground truth for the bias correction, and we look how a smaller ensemble can lead us to the spread and to the mean and standard deviation of a larger ensemble based on the full ensemble ENS10 business here. So you can actually use this data set. We've made it available to machine learning researchers who are not meteorologists, published at the NeurIPS conference, which is Neural Information Processing Systems. It's one of the top conferences in machine learning, where we really make all this data accessible to the wider community such that they can contribute new ideas how to help with these things. And again, these are all obvious things. This is just really summarizing the data, and I'm slowly running out of time. So this is why I need to go a little bit faster. So the setup itself, the learning setup, how does a deep neural network look like? Well, we feed 7 variables into the model. It actually doesn't matter. It could be 13, it could be whatever. We just chose 7. You can change those as you like. At one pressure level, we could also run multiple pressure levels. We concatenate them in a field and really do a very standard machine learning setup where we just feed in various data and then have a training ground truth. That is the error 5 reanalysis or the spread of the trajectory 1 to 10, where we only, on the uncertainty side, we only feed in 1 to 5. So we feed in 5 trajectories, and we want to predict the spread of all 10 trajectories. That's the setting for the uncertainty. The setting for the bias correction is we feed in the mean of the trajectories, and we want to get to the error 5 result. So we just train 2 different networks on this, and it's very, very standard machine learning. So the uncertainty quantification network is a variation of ResNet, very, very, very simple. So that's data from, or ideas from 2019. We would have chosen vision transformers today, and I'll get to those in a minute. The bias correction network is a 3D UNet, also 2019 technology, performs reasonably well. And actually, it's using a locally connected network. That's also quite important. So a locally connected network, in case you haven't heard this, is very much like a convolutional neural network, but for each of the points, it has different weights, right? So the filters are different for each point in the real domain, which is very nice because now the model can learn where a mountain is or where the sea is, so I don't know, local properties of the topography underlying. Okay, well, the training setup is also very standard. We have relatively good results. So the results are, if we compare to the 10 ensembles minus the 5 ensemble prediction versus the 10 ensembles minus normal 5 ensembles, right? So this is just choosing the mean of 5 ensembles. We get a 15% improvement in the accuracy of the model. For temperature at 850, for Z, so geopotential, we get also a 15% improvement. Then the bias correction also gives us like single-digit improvements. So Peter Dubin tells us that is a good result. And again, I have a hard time interpreting those results. So these are all RMSE numbers. We should talk about loss functions and how to assess differences between models in the break, because I'm very interested in this as a machine learning person. It is quite hard for me to understand what a good metric is, whether RMSE or MAE or other metrics are good. So then we have a lot of these meteorological pictures, and they just show that the accuracy of our learned models is slightly higher than the accuracy of the baseline models. So again, downstairs is a poster which probably improves upon those results, so I don't want to spend too much time on those. Okay, intermediate conclusions is actually very simple deep learning, very, very simple deep learning can already help improve the accuracy of ensembles. It can actually help to reduce the number of ensembles in a calculation, and it can also help to correct the bias. This is, I would call this a 0th step. From there, we could go, and you've been doing this the last years, we could check what has happened there. Okay, then one idea that I really like, I want to really communicate here, which is something where machine learning people would get a heart attack when they hear about it. So what we tried to do is we tried to look at the compression problem. And there's an interesting observation. What you could do is you could actually take your field, and you see it's relatively smooth. You could just take your output data field, and you could learn a deep neural network that reproduces exactly that output data field. This basically means we're completely overfitting that network to that particular data. But if the purpose is to simply reproduce this data in a compressed representation, then overfitting is fine. It was so surprising that to the iClear machine learning folks, because usually in machine learning, overfitting is the worst thing you can get. You try to avoid it at all costs because you want to generalize. But if you fit a data set, you don't want to generalize, you want to really represent that data set. We call this data as a function. We compute a function that produces a data set, and this function is a compressed representation of this data set. So they were so surprised that they put us in the top 5% of the one of the best machine learning conferences. So because it's a completely different view on how to use machine learning. So sorry, I should have advanced these slides earlier, but the idea is really to compress this multidimensional data into a neural representation. So this is actually quite nice. We can achieve a compression factor of up to 3,000 times without losing too much accuracy. Of course, you're having a certain smoothing effect. And since I'm running out of time, I don't have enough time to explain this. Here is also a talk of my student online, which you could watch if you're really interested in all the details. Here's the data set set up. Here is some data which is interesting because we get really much lower RMSE and also maximum absolute error compared to all other compression schemes like SC3, which used to be the best one so far. So the higher absolute error is also, the maximum absolute error is also good, but the maximum absolute error is slightly worse than the average error because of the properties of the model we are using. I didn't really talk about the model. The model is a Fourier basis network. It's derived from ForecastNet, the first version of ForecastNet without the spherical representation, and it thus smoothens out a whole lot. So just to show you some pictures, we have a reference version that is uncompressed. We have our version that is 1,000 times compressed. You can see there's nearly no difference in this field view. But if we run SC3 just at 400 times compression, we see a lot of artifacts here, right? So now you may say, wow, this is great. Well, let me show you some not so great result as well, because we want to be honest, we are scientists. There is a Hurricane Matthew here. In our 1,000 times compressed representation, well, unfortunately, Hurricane Matthew is not a hurricane anymore. It's like a slight wind. And in the SZ3 representation, it gets better, but it makes everything else worse. So we now have a new paper, a new representation coming up, which combines the two to actually capture high frequency, high difference effects together with the low frequency effects in a single model. Okay, so I want to skip this one. There's a spatial mixture of experts. I would highly recommend to check it out, but I was hoping to get some questions, so I can't talk too much about this. This is an idea how to make CNNs or LCNs better. In Weatherbench, with this idea, we actually beat all the existing prediction schemes in all metrics. So also in this example, this spread prediction example, we are significantly better. You can see here this SMOE and the UNets gets from 76 to 68. And here we go for VITs, we beat them quite significantly, 288 to 26. And the results are extremely good. But again, I don't have enough time to talk about the details of the model because I want to take some questions. So just to summarize, I've been talking about the EVE effort at the very beginning from a technical perspective. How do we, what do we want to achieve from a climate science? How do we get towards kilometer scale? I told you about our ideas of performance metaprogramming. So how can we optimize unchanged code in the latest version, even Fortran code? I would have not believed I would say that at some point. So it's really aimed at Python. Here, this is a performance metaprogramming for Fortran. And then I told you a little bit about the compression, which I still find is an extremely interesting field of research we could be getting into all together. And with that, I want to close. So join us in case you want to do an internship with a computer science group or being an academic visitor. We are always open. We have a lot of collaboration with climate folks. We have a wonderful office now in the 17th floor of a building in Zurich overlooking the city. So thank you very much. And I'm open for questions.
Thank you very much for this lovely talk. I just want to say that I envy your students. Do we have questions from online? Questions? There? Can I? Thank you.
I stole one microphone. I apologize.
Thanks a lot for the great talk, very inspiring. For the member expansion or inflation method, what do you use as an input? Are these the final ensemble run or all the steps? And I think, I did not get it completely, but you are not using an emulator inside, and would that be an alternative to have emulator running the other trajectories?
The answer is yes. So this is what I mentioned at the first part of my talk, which is very decoupled from the later part. So yes, for the ensemble prediction, what we simply use is we use 5 ensemble members and predict the spread of 10 ensemble members directly learned on that training objective, so CRPS. For what we are planning to do in the EVE context, is actually slightly different, where we use weather forecasting from a smaller number of deterministic ensembles run with a real simulation and use short-term predictions with deep neural networks that really replace the whole thing. Right? These are two different approaches. They could be combined to get a better sample of the real probability distribution, but that is to be seen. But yeah, thank you for the question. That's great.
Okay. Thank you. Other questions? There. Thank you.
Thank you. Yeah, thank you for your talk, also from my side. So my question is, when I see these deep learning efforts and these sets of variables that you choose for training, this reminds me of the various numerous papers in classical simulations where people claim that you should use total energy or you should use potential temperature. And I wonder how you settle upon this very initial choice of this specific equation or a variable set.
Yeah, I wonder too, to be honest. It is daunting. So our approach was ask the expert. In our first experiments, the expert was Peter Dubin, who told us that a geopotential at 500 meters is a good idea. So we did it. As I said, we are no experts. And this is actually quite funny. I'm working with many computer scientists. Now we try to really predict all the fields, because why would you make a subselection? For the compression, it's pretty funny because, as you know, precipitation has very high gradients, so it would perform probably relatively bad in our method, or also other local effects. But these are always at the surface, so they don't really matter for compression too much because it's only a 2D field, it's super small anyway, and we can quantize it. So we are very engineering driven in this sense. So we just exclude certain fields based on, does it make sense to compress them or not for the compression case? For the learning case, that's a completely different discussion that we ask the domain scientist. And I agree, it seems like a random, pseudo-random subsample of these variables, domain scientist.
Thank you.
Somebody back there. Sorry.
Hi, thank you very much. This was really interesting. As somebody who has been thrown into I/O and storage recently, I would like to chat with you about the data compression method during the coffee break. But to come back to the question of Fortran and all these languages, basically, I think what we need to do is to redesign STEM degrees. Our STEM degrees are not fit for the purpose of the modern technologies. This is just my opinion, because in the traditional meteorology, you learn numerical methods on a structured mesh, on a stencil, and the natural representation to represent that mind map is Fortran. Yep. This is why it's still there. And people don't have enough headspace to think about the data footprint of numerical methods. When they do their degree, they're focusing on convergence, stability, and so on. And then you have the computer scientists who don't really look at these, how you combine mesh and method to actually get to the data pattern. You only get the data pattern. What we need is something in between, a sub area of either a meteorology degree or physics degree or computer science, or some kind of a hybrid, which will cover that.
Oh, I completely agree. Thank you. It was more a statement than a question, but I want to comment on it. I couldn't agree more. I think we should do it from both perspectives. We actually at ETH, I'm teaching in a track that is called Computational Science and Engineering, so CSE, which is exactly in the middle. So these are performance engineers at the same time as domain scientists. And this is pretty funny because my students understand more of the domain than I do, and I hopefully understand more about performance. And so in the talk, I was going for a separation of the two. Right? So I wanted to introduce a very clean interface with these graphs where the performance engineer would not really have to work with the domain scientist. I don't want this to be misunderstood. I think this separation is great, but the separation is on a code basis. What you were alluding to is, how do I develop good algorithms that actually make sense from a performance perspective? That is a completely orthogonal problem to what I talked earlier about, and that requires experts in both fields. Like you need to have a certain expertise in both fields. So there's the code aspect, which I believe is separable. There is the domain algorithm aspect, which I would agree is very hard to, I don't see how to separate it. It may be separable, but I'm not an expert. And then you even alluded to storage and data representation. Oh my God. Now we need to talk about data structures and how data is stored. And I'll be talking for the next 10 hours and you'll be shuttling me out of here. So yes, the answer is yes.
Thank you, Torst. We have a question online. Martina Tudor has written in and asked, you explained the separation of concerns where the scientist is not really looking into the code or the coding, and the code translation is left to the computer scientist. The resulting code, however, might only be machine readable.
Mm-hmm.
Assuming the computer scientist is also human, how would the process of translating the scientific ideas into computer code and testing those ideas work in the future?
Well, I mean, thank you for the question. The future vision is really that the performance engineer, who is also a human, yes, actually, and that's a good question. Is the performance engineer always going to be a human? I believe partially. So I showed you the method about transfer tuning. I didn't go into detail. The transfer tuning method is actually based on reinforcement learning, representation of vectors, and I didn't show you the neural network doing it, but it is based on a neural network that replaces parts of the human. But the human would still need to identify, at least today, maybe we can replace that as well, the common subsets of the program that I mentioned, these graph cutouts. Right? This is what a human does. And there is no magic in this whole tool chain, because most people think, oh, you click a button and it's going to work. No, no, no. It's very hard work. You click a button and then you get a graph representation, which is unintuitive for many and relatively intuitive for a performance engineer. Like, this is the same thing. If I look at your code, for me, it's unintuitive what the math behind this is, but the data flow is intuitive to me. So we really have a separation of expertise among the humans. And how this is going to be in the future? Well, I hope that the humans will learn to deal better with this data flow representation such that they can map things better to architectures, to underlying architectures. For example, now we are working on mapping to Cerebras systems, which is quite hard because it is a very large two-dimensional chip. It's a spatial computer. So you're now suddenly worried about where your data resides for every single data item, which is not so important on a GPU, even though the Hopper architecture already has kind of two islands that are not so strongly connected. So it goes towards spatial architectures as well. So that's going to be the next challenge from a computer science perspective, mapping codes to spatial. And it's very tough, I would say, very tough for humans to think in that mode.
Okay, thank you very much for the questions and for the answers. And in thanking you very much for this enlightening talk, and I think that we as SMWF will get in touch because of our new project on the machine learning, and you already saw how well it fits with what we have. Just a small sign of our appreciation, so you don't forget us. You will look at it and you will remind. It's the new mascot of SMWF. Thank you very much once more. And